Hi, so welcome to another lesson of linear transformation. Okay, so we are actually going through a lot of proofs of some theorems which we may use in the future to write other proofs as well. Okay, so let V and W be vector spaces and let T such that V maps to W be linear. Then T is one to one if and only if the null space is equal to the zero vector. Now let's write a proof to it. Okay, how do I prove this? Now, suppose T is 1 to 1, right? So we have an if and only if proof here. One thing we want to prove is that if T is 1 to 1, then, so for if and only if proof, we prove it this way. There are other ways you can use to prove it, but I mean, mostly we follow this approach. Then the null space of T is equal to the zero vector, right? And two, if the null space of T is equal to the zero vector, then T is 1 to 1. Right, so these are the two things we want to prove. Now let's prove one. That is this direction, right? The 1 to 1 implies is the null space of T being 0. So suppose T is 1 to 1. What do we want to prove here? Then we want to show that the null space of T is equal to 0, right? Then and have some x being a vector x in the null space of T. All these things, and the 0 here is a vector, x is also a vector, right? But I'm just, for clarity's sake, I'm just writing as x here. Then what can I say? Then what is the transformation of x? Because x is part of the null space, is equal to 0, right? And we know that T is 1 to 1. What does it mean? Right? What does it mean? 1 to 1 means that if I have, I'll clean this. 1 to 1 means that if I have something here, right, and it maps to another thing, this should map to only this 1 to 1, right? If I have some k here, it should also map to some other thing here, right, and not map to any other thing. So it maps to exactly one thing, right? What does it mean? It means that it implies that we also know this. Before I go to that part, we know that if T is linear, we know T of 0, the 0 vector is equal to 0. What does it imply? It implies that x should be equal to 0, because for every linear transformation, the transformation of the 0 vector gives you the 0 vector, right? So, and then T is also 1 to 1. If it is 1 to 1, it means 0 maps to the 0. So for every vector x you pick in the null space, that vector should be the 0 vector, right? That's what it means. So it means that, so this x that we picked was arbitrary. So it means that the null space of T should be equal to just the 0 vector, because we just intentionally picked some arbitrary x, and it turns out that that x must be 0. In order for T to be 1 to 1, it means that that x should be 0, right? So we have that part proved. Now let's go to the other part that says that suppose we want to show that if the null space of T is equal to 0, then T is 1 to 1, right? Suppose that the null space of T is equal to just the 0 vector, right? And how do you show that something is 1 to 1? I mean, these proofs actually also help us. Well, you can, what I'm proving here, how I'm proving the if and only if problem, you can actually apply it in every aspect or every setting of math. If you have a problem that involves 1 to 1, you can use this approach. The first thing implies the last one, and the last one implies the first thing. Okay, and also there's a particular way of proving that something is 1 to 1. We are going to show that if t is 1 to 1, want to be able to show this. Let's see. I want to. This is how the 1 to 1 proof goes. That if so, to show that something is 1 to 1, if t of x is equal to t of y, then we'll have. Let me clean this. Then x is equal to y. That's what I want to show. For 1 to 1, if I say that it's like you having a function, if f of x is equal to f of y, this will be 1 to 1 if x is equal to y. That's the case, right? So if that happens, so we want to show that if t of x is equal to t of y, then x is equal to y. And also suppose that we know t of x equal to t of y. We want to be able to show that x is equal to y. Then you can do this. T of x, we know that t of x minus t of y is equal to 0, the 0 vector, right? Now this is linear transformation. T is linear, right? It means that we're going to have t of x plus t of negative y, right? This negative 1 in front of it is equal to 0. And we know as well that t of x plus t of negative y can be written as t of x minus y, since t is linear. And what do we have? We have t of x minus y being equal to 0. What does it mean? It means x minus y belong to the null space of T. And what is the only vector that is in the null space? It means that x minus y is the 0 vector, because the null space of T is 0, is the 0 vector, right? So it means that x is equal to y. And that ends the proof. That shows that indeed T is 1 to 1. So we are done with the proof. If T is 1 to 1, T will be 1 to 1 if and only if the null space of T is 0. Because here we've been able to show that if T is 1 to 1, then the null space of T is 0, the 0 vector, and that is what we showed. And then if the null space of T is 0, then T is 1 to 1. I mean, this is a very crucial result as well. Just keep it and have that in mind, okay? So thank you for staying with me. We'll talk about some other theorem in the next videos, okay? See you.